Hi, welcome to my topic Circuits and Networks. I am Ravikant Malla Joshua, and today's session we are going to have Norton's theorem, and this particular class will be treated as class 1 under Norton's theorem. When you look at the definition of Norton's theorem, it states that any two terminals of a network can be replaced by an equivalent current source in parallel with an equivalent resistance. So this is how Norton's equivalent circuits look alike, where you have I Nortons and R Nortons. How to find I Nortons and R Nortons is a challenge. So I Nortons is also known as short circuit current. So wherever it is required to find, we need to find out the short circuit current, and that becomes the Norton's current. And then we need to find out Norton's resistance, which is nothing but equivalent resistance of a given network. Let us start with the problem. In this approach, you can see we have 120 volts driving this circuit, and across this PQ terminal, we need to find out Norton's equivalent network. So for that, we need to find out short circuit current, and we need to find out Norton's resistance, which is also known as equivalent resistance, and it is quite similar to equivalent resistance under Thevenin's theorem. So let us find the short circuit current, which is known as Norton's current. So you can see the PQ terminal is where the open circuit is there. There we have shorted the terminal. So this becomes the short circuit current. When 120 volts is active, what is the short circuit current over this particular point? Now this can be done with many ways. You can apply any method to find out the short circuit current. We have KCL, KVL, we have current division rule, or any network reduction technique, or standard mesh analysis or node analysis. So you can apply any of these methods to find out the value of short circuit current. Then what? We need to find out Norton's resistance. As I told you, that is nothing but the Norton's resistance, nothing but the equivalent resistance of the network. And if at all you have the voltage source, that is need to be shorted, and if at all you have current source, that is to be open circuited. So this is a familiar thing which we have done in Thevenin's equivalent circuit. There we have found out Thevenin's resistance. The same approach we are going to employ for Norton's resistance. So let us start with the problem. So here I am taking node analysis. I am identifying the node voltage as V1 and V2. By clear inspection, 120 volts is parallel to 52 ohms. So V1 will be equal to 120 volts. Is this clear? Yeah. Now we need to apply node analysis at this point, which is designated by V2. So it's the KCL states that the algebraic sum of the currents at a particular node is equal to 0. So we'll follow that. So V2 minus V1 by 40, this is one branch current. V2 by 10 is another branch current, and V2 by 3, which is equal to I short circuit, that is another branch current. So this satisfied the KCL. With this, I'm going to get the value of V2, which is equal to 6.67 volts. Once I'm going to get the value of V2, it is easy for me to obtain the value of short circuit current. Therefore, the short circuit current is nothing but V2 by 3. So this current is nothing but the branch current which is flowing from this point to this point. So 6.6 by 3, which is equal to 2.2 amperes. Now this is the equivalent current which we have obtained with the help of V2 by 3. That is the short circuit current, also known as Norton's current. Now let us calculate resistance R equivalent across PQ. As I told you, when this is shorted, this 52 ohms has no impact, so it becomes dummy resistance. Therefore, RPQ, it is obtained as the combination of the rest of the resistors. So you can see 40 is in parallel with 10, and the resultant is in series with 3. So I'm going to apply the values, and resistance is obtained as 11 ohms. This is also known as Norton's equivalent resistance or Thevenin's equivalent resistance. So the approach is same whether you apply for Thevenin's theorem or Norton's theorem, particularly in the case of resistance. Now once the values are obtained, I'm substituting the value of Norton's current and Norton's resistance. Therefore, that becomes the Norton's equivalent circuit or network for the given network. Let us go with the different example. Here you can see we have dependent source 5Vx. It is known as voltage dependent voltage source, and that voltage is being measured across 2 ohms. Okay, positive is aligned over here, negative is aligned over here. So carefully inspect the circuit or network. To find out Norton's equivalent network, we need to find out the short circuit current, which is over here, and Norton's resistance. When you have dependent sources, the way in which we have followed Thevenin's theorem, the same thing we have to follow for Norton's theorem. Since we have dependent voltage source, we have to find out the open circuit voltage across this terminal, and we need to find out the short circuit current. So the maximum voltage and the minimum current which is flowing across this terminal will give you the value of the resistance of that particular terminal. So let us concentrate on this resistance. So this is a circuit, and as I told you, when this becomes open circuit, when this is open circuit, this 4 ohms becomes dummy because the current is not flowing in 4 ohms. It is open circuit. But we have dependent voltage source. 5Vx is the dependent voltage source, and Vx is represented over here. And since it's open circuit, it's a single turn circuit. This 2 amperes will flow in 2 ohms directly. So we need to find out the open circuit voltage over here. So I'm applying the mesh analysis. You may be wondering why I'm applying mesh analysis. Since I have voltage here, I have another voltage here, and I need to know this voltage. So neglecting this resistance, I'm taking the rest of the voltages. So first, let us find out the Vx. Vx is nothing but the current which is flowing in 2 ohms. 2 ohms is having 2 amperes. So this becomes 4 volts. This is clear? Right. Now minus Vx minus 5Vx plus Voc equal to 0. As I told you, dummy resistance is being neglected. So I'm going to get the value of Voc by taking the value of Vx as 4 over here minus 5 times of 4. This becomes 20 and this becomes 4. So minus 24 value will be replaced over here. Therefore, Voc is equal to 24 volts. Simple. Now once open circuit voltage is obtained, let us find out the short circuit current. So the same terminal, I am finding out the short circuit current. So this is the short circuit current. Now we have now two closed loops in this particular circuit. So I'm taking the I1 and I2 in these directions. I1 and I2 are taking these directions. The loop currents I'm taking according to my own wish. You can have your own directions. With this estimation, I can strongly say that I1 is equal to 2 amperes and I2 is equal to I short circuit. Is it that simple? So once I'm going to get the value of I2, I can easily obtain the value of short circuit current. So I'm applying mesh analysis to the second loop. No need of applying mesh analysis to loop 1 because we know that I1 is equal to 2 amperes. So I'm starting with 2, assuming this loop to be the dominating loop, 2, I2 minus I1 plus, now we have to consider 4 because the wire is shorted. So 4 has to be considered, 4 I2 minus 5 Vx is equal to 0, and this I'm taking as equation 1. Now what is this Vx? Vx is the established voltage across 2 ohms. So positive and negative symbols of Vx is given already. So the direction of current, what we have assumed, they are acting along with the given direction of the voltage. So Vx becomes strongly as 2 times I1 minus I2. With all these values, that is I1 is equal to 2, Vx is equal to 2 times of I1 minus I2. I'm going to get the value of I2, which is equal to 3 by 2 amperes or 1.5 amperes. Once I'm obtaining the value of I2, the short circuit current is obtained. Now, Thevenin's resistance, which is equivalent to equivalent resistance, which is equivalent to Norton's resistance, that is nothing but Voc by Isc. Substituting the values, we got the value of Voc as 24 volts and Isc 3 by 2 amperes. I'm going to get the value of resistance as 16 ohms. Now, once the values of the short circuit current and Norton's resistance are obtained, we are substituting the values and this becomes the equivalent network for the given network. So as you can see, we have identified two examples to understand the basics of Norton's theorem. In my next class, I'm going to take some more numericals, especially dependent sources problems, and we are going to find out the Norton's equivalent network and followed by maximum power transfer theorem. So if you like my video, please share among your friends subscribe to my channel, and please press the bell icon for the future notifications. Thank you.